Hello anatomy students. Today we are going to talk about bone growth, bone fractures, the healing process, and the hormones that dictate how bones form. So go ahead and open up your document that goes along with this lecture video and go ahead and pause this if you need to so that you can get yourself all ready, and then we'll begin. All right, so bones can grow in two different directions. They can grow lengthwise, longitudinally, or they can grow wider. They can increase in diameter. Let's talk about longitudinal growth first. So in order to talk about longitudinal growth, we have to first talk about the epiphyseal plate. So let me, in this diagram or in this picture, I just wanted to show you where our epiphyseal plate is, because that's going to be an important landmark for our bone. You see, on the epiphyseal side, which I'll highlight in blue, on the epiphyseal side of our epiphyseal plate, this is where new chondrocytes are going to be born. But on the diaphyseal side of our epiphyseal plate, which I'm coloring in green, here, this is where ossification of those chondrocytes is going to occur. So basically what's happening is that new bone is forming on the diaphyseal side of our epiphyseal plate, and that is going to push the epiphyseal plate towards the end of the bone. And the result is that the space, the amount of spongy bone that exists between the articular cartilage and the epiphyseal plate is going to stay roughly the same, constant all the time, because you're going to get this bone being laid down in this direction towards the diaphysis, and then that's just going to push this whole chunk further and further away. Now, this is occurring via endochondral ossification. There's a whole process to this that's in your reading, but that's going to be a different video lecture. So I really like this picture because it really goes into the detail of what the epiphyseal plate is. And as you can see, the epiphyseal plate is subdivided into 4 different zones. Now, you guys don't have to know the zones at all, but it is just kind of interesting to see that on the side of the epiphyseal plate, so this all 4 of these layers, pink, purple, teal, and white, all of them together, that is the epiphyseal plate. And so the part that is closest to the articular cartilage is called the zone of resting cartilage. The purple part is the zone of proliferating cartilage, so that's where the chondrocytes are dividing. The zone of hypertrophic cartilage is where these chondrocytes are starting to increase in size, and then eventually they undergo apoptosis, and then they are calcified here by our osteoblasts. So our old chondrocytes, the ones that are being pushed down towards that medullary cavity, they are replaced by bone. But the other reason why I really like this diagram is that if we just look at the epiphyseal plate from the left side to the right side, you can see that like the bottom parts of my brackets here and here, like the one that's over on the right is higher than the one that's on the left. And the reason why is because new diaphysis, the new bone, is pushing that epiphyseal plate up towards the end of the bone where the articular cartilage is. Now, I want you to note that longitudinal growth is only occurring at the epiphyseal plate, and the closure of this plate is gradual. So by taking an x-ray and by taking certain measurements, clinicians can determine how much more time an individual has to grow. Now, remember also that once the person has stopped growing, all of the cartilage, all of these chondrocytes are going to be completely ossified, and that's just going to become a bony structure so that no more growth can occur. And remember that the name of the epiphyseal plate at that point is going to change from epiphyseal plate to epiphyseal line. Now, our bones can also grow in thickness, which is going to increase the diameter of our bone. And it all starts at the periosteum. So I'm going to first outline my periosteum here in green. There. And I just wanted you to take note of some of the periosteal cells that are here in blue. So they live underneath, like between the periosteum and the compact bone that it covers. Now, what's happening here is that our periosteal cells, the ones that I highlighted in light blue, are going to become osteoblasts. And remember that osteoblasts build bone. They are the ones that are going to secrete the bone matrix. So they're going to secrete the subunits that form collagen. They're going to secrete the components of hydroxyapatite, which is the calcium salt that kind of collects around the collagen, making it very hard. And as the osteocytes secrete their matrix and they become trapped, they're going to become osteocytes. And all of this building of this bone matrix is going to form these curves, these periosteal ridges that you see here. So we've got ridges in the periosteum that are going to create a little groove for our periosteal blood vessel to just kind of nestle in. Now, what's going to happen is that eventually our periosteal ridges are going to fuse together. So here you can see that our cells here have formed bony matrix, and they're going to cause our periosteum, which I'm going to highlight in green here, to kind of come together. And what's happening is that they're forming a tunnel around that periosteal blood vessel. And this tunnel is going to become the new osteonic canal, which forms the center of an osteon. And that's what that blood vessel is. It's forming that osteonic canal. And the other thing that I just wanted to bring to your attention is if you take a look at this blood vessel here, this one is actually penetrating through that periosteum and going into the compact bone itself. That is an interosteonic blood vessel, and it's going to form the interosteonic canal, also known as the Volkmann's canal. So, what's going to happen now to this periosteum? Well, its name is going to change, and it's going to cease becoming our periosteum, and it's instead going to become the new endosteum that lines the inside of our osteonic canal. But notice that we haven't lost our periosteal cells. Our periosteal cells turned osteoblasts, right? And so what's going to happen now is that these osteoblasts are going to form bony matrix and deposit it here towards the center of that canal where our blood vessel is. And they are going to be forming new concentric lamellae, and that's how a new osteon is formed. So when bones grow in thickness, what's happening is we're getting new formation of compact bone. And so here the bone is just going to continue to grow outward as the osteoblasts in the periosteum build more and more concentric lamellae. And so as you can see, here is our new central canal, or Haversian canal, or osteonic canal. So remember that it's got a couple of different names. And then over here by this blood vessel, we have a new one that's starting to form. And you can see that here you've got this coming together of the periosteum itself. Okay, so the the bone is continually going to renew itself, because throughout life, we gain weight, we lose weight, we carry heavy things like your backpacks, we have different stress patterns, depending on what we're doing. Like, maybe you're going to live in a dorm where the elevator doesn't work, or there's always a long line, and so you've got to, run up the stairs all the time. And then maybe the next year you live in an apartment that has a working elevator, and now you don't have that stress anymore. So your bones are going to change according to the different stresses that you are putting on them. So in order for bones to change, they undergo a process called remodeling. Bone remodeling involves two different processes: resorption and deposition. Resorption is bone destruction. And you're probably like, well, why do we want the bone to be destroyed? Well, remember, it's kind of like sculpting, right? Like, think of the Michelangelo statue. It didn't just come that way. No, it started out as like a giant block of marble. And then Michelangelo had to go through and carve it out, had to destroy that block of marble in order for us to get the statue of David. So that's kind of what's happening with our bones too. We have bone cells called osteoclasts that are going to use different acids and different enzymes that are going to break down the bone matrix and release all of those materials into our blood. So our osteoclasts are the sculptors of the bone, whereas osteoblasts are bone building. So these two processes have to be balanced in order for our bones to maintain their proper shape, but also their proper proportions throughout our lives. If we just had osteoblasts that were just laying down bone and building bone and building bone, we would just have like these 2x4s for bones, and they wouldn't have the correct shape that they are supposed to have in order to perform their functions efficiently. And so our osteoblasts, as I mentioned before, are going to add minerals and collagen in order to form that bony matrix. And so how does resorption actually happen? Well, our osteoclasts have a really interesting shape. They look like little turtles, kind of, that have like this big rounded portion, and then they have this ruffled edge. And from the ruffled edge, they are going to secrete these enzymes that are going to break down the bone matrix that it comes in contact with. And these cells are going to absorb the bone matrix via endocytosis. So they're going to form these little bubbles, membrane-bound bubbles around the components of the bone matrix that they just broke down, and those little bubbles are going to travel through the cytoplasm of our cell, and then via exocytosis they are going to exit the cell and enter our bloodstream. And so the enzymes that our osteoclasts are going to secrete, they will digest collagen and other organic substances, and then they're also going to release acids that are going to dissolve minerals like calcium. So a couple of factors that are going to affect bone growth and remodeling are minerals, vitamins A and C, different hormones like IGFs, those are called insulin-like growth factors, thyroid hormones, androgens are male sex hormones, and estrogens are female sex hormones. All of these things are needed for the stimulation of osteoblasts and also the synthesis of collagen. But the one thing that I also wanted to mention is that, like, over time, androgens and estrogens are, they're going to start to slow in their production. And as one enters adulthood, resorption is going to slow down a little bit. Okay. So now that we know a little bit about the bone remodeling process, let's talk about some injuries that can happen to bone. And what I'm talking about here are fractures. And some of you may have some firsthand knowledge about fractures and what they're like, and looking at x-rays and things like that. And many of you probably have had some kind of surgery in order to repair a bone. But let's just talk about the different kinds of fractures that can happen. The first type that I have a picture of here is an open or a compound fracture, where a broken bone will pierce through other tissues like muscle tissue, adipose tissue, the cutaneous membrane, which is our skin, and now is going to open up the interior of our body to the environment. And, there's a number of things with open and compound fractures that clinicians have to be wary of, like infection, like damage to the tissues. And with that comes along a syndrome called compartment syndrome, where damage to the muscle tissue is going to cause a buildup of pressure because of a buildup of fluid inside of the muscle tissue. And what can happen is that the buildup of this fluid could put so much pressure on the muscle cells themselves, on the nerves themselves, that it can cause damage and leave the person impaired for the rest of their lives if it's not fixed properly. So open compound fractures are quite serious injuries. Now, the next fracture that I have here is something that's called a compression fracture. And compression fractures are typically used to describe fractures that happen in the vertebrae. And as you can see here, you have basically the body of one of the vertebrae is being squished. And you can see that it's much thinner than it ought to be. And this can be because of an injury, like maybe somebody had a fire in their building and they had to jump out the window and they landed square on their feet, and just the force of that impact caused, their bone to break. But more often than not, what is actually happening is that the person could have an imbalance where osteoclast activity outruns osteoblast activity, and that's exactly what happens in osteoporosis. You don't have enough bone building, but you do have a lot of bone resorption. And so, this bone could become very, very weak, and even just by, walking down the stairs, or by maybe, getting out of bed, too swiftly, like stamping their feet. This can definitely happen, and it happens especially in older people. So this is something that's called a compression fracture, and it could even just be that the weight of their upper body just becomes too much for their vertebrae to handle, and it just crushes that bone. And then these are a couple of other different kinds of fractures. A transverse fracture is going to occur perpendicular to the long axis of the bone. And a linear fracture is going to occur parallel to the long axis of the bone. We have two different kinds of oblique or diagonal fractures. One of them is where you don't have any displacement, but the other one is where you do. Now, you don't always have like this much space in between. This one looks like there's so much space in between that it could possibly be an open fracture, but they don't always have to be. Now, a spiral fracture usually occurs when like one side of the limb is planted on the ground, but the other side gets twisted. And so that's what a spiral fracture is. Usually that can occur like in sports, football, like if the player's foot is planted on the ground and then they get tackled and their upper body twists, but their foot stays in the same place. That can happen in soccer as well. It happens in both quite often. Now, a green stick fracture is especially interesting. This is one that happens mostly in children. And maybe some of you have tried to maybe take a limb off a tree and you try to bend it. and it doesn't break. It just kind of bends. And if you look at the inside of that limb, it's still green because it's still alive. Well, that's what happens a lot with children. They are not fully ossified yet. And so their bones are going to bend instead of break. So in a green stick fracture, what happens is one side of the bone will break, but the other side bends. So notice that this side, it's not broken all the way through. The one side will bend while the other side will break. And then the last type is a comminuted fracture. And again, this is similar to a compression fracture, but when it happens in an extremity, they call it a comminuted fracture. Sometimes what can happen is that like it can be impacted where like this portion of the bone can actually like smash into the other portion of the bone. And so a comminuted fracture can also occur like if somebody falls and they put their hands out in order to break their fall, that can cause a shattering of that bone as well. And so once a fracture occurs, now the body is going to start working in order to repair it. But in order for bone repair to actually occur, there's got to be bleeding. And this is just like with wound healing, everybody. Like with bleeding comes inflammation, and you're going to get the arrival of cells that are required in order for repair to occur, like fibroblasts. So anyway, that's got to be the first thing that happens. And I'm going to go through all of these in a little bit more detail, but basically we have the reactive phase that happens first, the reparative phase that happens second, and there are two different events that are happening in the reparative phase. And then finally we have the bone remodeling phase, which is what we've already kind of touched upon, what bone remodeling is. So remember, bone remodeling is going to happen all throughout life, but it's definitely also a part of the repair process that happens once an injury to bone actually occurs. So in our first phase of repair of a fracture, we have a reactive phase. And the first thing that happens is bleeding, and we get what's called a fracture hematoma, which is basically a bruise. And it's caused by blood vessels in the middle of the bone being damaged, which is what we have here. And the blood is going to start to leak out. Remember that these damaged tissues are going to start sending SOS signals to the immune system so that you can get macrophages and neutrophils and other cells to the area in order to keep infection out of the area. But the other thing that a lot of these macrophages and neutrophils are going to do is they're going to take these dead bone cells, the dead osteocytes that have died now as a result of this trauma, and they're going to start to remove all of this dead and damaged tissue. So those are the two things that are happening during our reactive phase. As I said, during phase 2, which is called the reparative phase, we have two events that are happening. The first one is that a fibrocartilaginous callus is going to form. And by bleeding, the blood is going to bring with it some fibroblasts into the area. And recall from our wound healing that fibroblasts are going to lay down collagen. We're also going to get from the blood some cartilage precursors called chondroblasts, and these cells are going to start to lay down some fibrocartilage, which again has a lot of collagen in it. So fibroblasts and chondroblasts are going to enter the area, and they are going to create like a mold or like a cast to try and stabilize this fracture, and they're forming what's called a fibrocartilaginous callus. In event B, what happens is that osteoblasts in the area are now going to ossify this fibrocartilaginous callus. And what we get, number 2 here, is the formation of the bony callus. So osteoblasts are going to ossify the fibrocartilaginous callus. And they're going to do that by the formation of spongy bone. And then finally, we have the bone remodeling phase. And now our osteoclasts, again, the sculptors of our bone, they are going to smooth out. Like, notice how smooth this is now. Like, we have a little bit of a bump over on the left, but it's all getting smoothed out. And the reason why is because osteoclasts are going to start to sculpt that down, get that bump out of there, because we don't want it. We want the bone to heal as close to its original form as possible. And then we are going to get compact bone being formed in place of the spongy bone that the osteoblasts had laid down around the periphery of the fracture. And that's going to allow the bone eventually to become just as strong as it was before and to withstand just as much stress as it did before. And so, like I said, bone remodeling, it's happening all throughout life as your life changes, as you grow, but it's also a part of the repair process. All right, so we've got two main hormones that are going to help in maintaining calcium homeostasis in the body as well as in the bone. Now, remember that bones are a reservoir. They're a storage site for calcium. And the first thing that I wanted to call your attention to is this graphic here in the upper left. Our muscular system, our nervous system, our cardiovascular system, they all need calcium in order to function properly. But just like anything else, you don't want too much calcium, otherwise it's not going to work out well. So that's where our endocrine system is going to come in. So our endocrine system is going to help to regulate how much bone or how much calcium, we have in our blood. Now, when blood calcium levels drop, our endocrine system is going to stimulate the release of parathyroid hormone, or PTH. Now, parathyroid hormone is coming from some tiny glands that are found on the posterior aspect of our thyroid gland. Our thyroid gland is found in our neck, right? Sort of around where our larynx is. And when stimulated by parathyroid stimulating hormone, the parathyroid hormone will release PTH. PTH will stimulate osteoclast activity. So remember, PTH is going to be released when blood calcium levels are low. So when we have low blood calcium levels. When we have low blood calcium levels, PTH is released. It stimulates osteoclast activity. And that should make sense to you because osteoclasts are going to break down that bone matrix and release calcium into the blood. So that's going to cause an increase in blood calcium level so that it can be used by our other systems. Now, the opposite can also occur. We don't want to have too much calcium in our blood. So when our calcium levels go up too high, we have the release of calcitonin. So calcitonin is going to be released when we have high calcium levels in the blood. And calcitonin is going to inhibit osteoclast activity. So it's going to stop the breakdown of bones, stop the release of calcium into the blood, and instead it's going to stimulate osteoblast activity. It's going to get these cells going so that they're taking calcium from the blood and putting it back into the bone for storage. So calcitonin is going to decrease blood calcium levels, and again, in order to ensure that our muscular, nervous, and cardiovascular systems are working efficiently. The last thing that I just wanted to mention here is that calcitonin, unlike PTH, calcitonin is synthesized and secreted by the thyroid gland, whereas PTH is synthesized and secreted by the parathyroid gland. And then the other thing that I just want to mention is this. So parathyroid hormone is going to stimulate osteoclasts, but it inhibits the osteoblasts, whereas calcitonin does the opposite. And the way that I remember what these do is I just remember what calcitonin does. And if I look at the word calcitonin, it calci to in. So calcium is being brought into the bone. And I know it's kind of silly, but it definitely helps me to remember, because I know that calcitonin and PTH are opposites. And if I just remember that calcitonin puts calcium into the bone, then I know that PTH is going to do the opposite. Okay, and then the last thing that I just wanted to make mention is that stress is going to make bone stronger. It's kind of like a use it or lose it kind of scenario, right? So as you put stress on your bones, like when you run, when you lift, you are going to increase the deposition of mineral salts into the bone, thereby making them stronger. You're also going to stimulate osteoblast activity, and it's going to it's going to help to build up that bone and those mineral salts. The other thing that it's going to do, though, is it's going to stimulate bone remodeling. And so it's also going to ensure that osteoclasts are working properly so that your bones maintain the correct proportions. High impact exercise will stimulate bone remodeling more than low impact exercise. And adolescents just need to be very careful, when you're weight training and building mass before that epiphyseal plate closes. So, make sure that, you don't want to start weight training when you are too young, because that can interfere with growth plate activity. All right. Oh, sorry, I hit my pause button there. All right, so that's all that I have for you today. Thank you so much for listening, and I hope that you learned something today and that you enjoyed it. Have a great day, and I'll see you in class.